snowfall?
I don't know.
We can look at it.
Never looked it up. I bet it's
Half inch?
half inch. That's, yeah, it's got to be right. What'd you get more on the hill? No.
Half inch?
Yeah, that's about all we had. But it was okay. I'm not complaining. It was all right.
It was a nice solid snow. It wasn't a shower where the temperature's below freezing.
Yeah, that's right. It was 27 when it was over.
Yeah.
So it was pretty darn cold for that.
The dogs enjoyed
We're
it.
about ready to go. Yeah, sorry, a little bit of a delay. We had a computer issue, surprisingly.
Well, it was minor. It was more getting this 5B set up.
It was a security.
There's a lot of cool stuff.
It was actually a security issue. If you'd like to view my email, all you have to do is log into your account on UW and you'll probably get there.
Did you get one of those little things already?
Not yet, no. The multi-authentication, whatever it is.
Yeah,
Multi-factor.
Multi-factor authentication. What's the whole thing?
Multi-factor. Yeah.
Authentication what? There's another word. There's a fourth word. Oh, rollout. That's what it was. Because Chelsea had it on the agenda. Rollout.
I'll get it. I'll figure it out. Okay.
Okay, let's leave the fire stuff till later. Michael's going to give a discussion about the fire, which is a major issue, of course.
I have a burning desire to talk about it.
Yeah, just briefly. He's in fuego about it. Let's start with our satellite movie over the continental United States. Leo kindly noticed my tie, which has snowflakes on it today. And we had our first measurable snow last night, which was very exciting. Actually, I don't know if that's true. Maybe we had it on the 20th of October in that 1 hour snowstorm. That might have been qualified as measurable. But, you know, I agree with Greg. This was the first real snow because it stayed around after it stopped snowing. And it was about a half an inch, maybe at my house, same on the hill in Middleton.
It's going to bring up the Madison on.
Okay.
What do I see?
Probably less than 6 inches at the airport. So they tend to inflate the amount, in my opinion, from what I always get at my house.
It depends on what they predicted.
Yeah, well, that's right. That's unfortunately quite true, I think. So we're at 0.01 I saw somewhere. Where's the stove?
Okay, so if you go to the 12Z, so 1153 or so, scroll up a little bit, 1153, 1 inch. Officially the first inch of the airport.
They must have predicted
1
that.
inch.
Yeah, right,
I don't think there was an inch of snow around here.
right here. So this is the fore group, is the snow and ice. And that's an
And
inch.
do they round up after half an inch, or what do they put? No, honestly, I mean,
Yeah,
sometimes.
that I don't know, but
Yeah.
the liquid equivalent was 0.05. So it's,
Okay.
Half inch.
yeah, but it's a fluff factor. I don't know how fluffy it was. But
Yeah. Okay, so, but anyway, that's the first time that we've seen an inch show up in the odds for this year. And that's relatively early, I think, because I think the average first inch of snow is more like the 18th or so of November. So we're about a week in advance, and we're doing it in a relatively warmer world than the period of time during which that chronological average was set. So that's interesting. It certainly hasn't been warm around here. And it's not going to be warm for the foreseeable future, a few days anyway. And we'll take a look at all of that stuff as we go forward in the forecast and the discussion of the weather. But here's a visible satellite with fake news green and blue color on top of it. But actually, that's not true. It's really, they do a pretty good job of that, right?
pretty close to it.
Yeah. So here's our view over the continental United States and parts of South America and Central America. And you can see a pretty decent cyclonic disturbance, and more than one has moved across the eastern part of the United States during this week. And so as a result, there's been a baroclinic zone draped across the southern United States for much of the last couple of days. And you can even see here a couple of shadows early in the morning of higher cloud, probably convective activity. We'll have to check and see that on the radar. That was certainly the case yesterday, late in the day. So, but only scattered convection. The frontal structure down to the southern United States has kind of fallen apart a little bit. Certainly the dynamics of it has fallen apart over the last couple of days as they've moved forward. So, but you can see the cooler, drier air settling in across Texas and eroding some of the low-level stratus clouds that the day, with which the day began in the northern half of the state or so.
John.
Yeah.
It's also interesting, not only in the Rocky Mountains can you see the snow that's in the peaks there, but also you can see tracts of snow over parts of northern Kansas, Nebraska.
Oh yeah, Nebraska. That's one for sure. That's another. Yeah. Yeah, so it was interesting. Yesterday, we were in 452 watching this sort of a clump, an amorphous clump of precipitation in the radar. It just had that funny, fuzzy, bluish look around the edge of it that made me think it's some of that snow. And we looked at surface obs. Sure enough, quite a bit of it was snow. And then here is the residue at the surface. So this is a large part of Kansas with snow on the ground and a nice, very mesoscale strip in Nebraska and another one to the north. So quite interesting. And even some snow, of course, in our own state, in the northern part of the state, it looks like across, around Wausau and maybe a little further north of Wausau.
I think it was interesting that the models consistently were predicting this snow going back almost a week.
Yeah, I think you're right.
And forecasters ignored it up until yesterday.
Yeah. It's interesting. I told your class last Friday that today was going to be a really cold day with maybe some snow. And so I had to make that up myself. It was informed by the forecast models. So sure enough, that turned out to be true. Isn't that interesting? It's a whole week ago. Yeah. So what I want to show you today in the current weather, and I'm going to do a little bit of a peek at the forecast, we'll do it with Viz 5D, is what's hard to actually see on this map as it stands is that there's a bitterly cold air mass poised just to our north. In fact, it's already invading. So, and it's very, very cold. If this were January, we'd be looking at record cold temperatures. I think we may even be looking at record low 850 millibar temperatures. I don't know what that value is off the top of my head, but it's very, very cold over the central part of Canada and invading the northern United States. Part of that whole synoptic evolution involves a series of little waves that have come along the western side of the cold dome. One or the other of them have kind of developed into upper vortex structures through upper frontogenesis. And the last one in line is going to turn into over this short forecast period, turn into a very potent upper disturbance, which will then nurture a cyclone development over eastern Canada that's going to get quite intense down into the 970s. So that'll be kind of an interesting story, especially because the upper vorticity structure takes a long time to really mature into a strong upper vortex, and it happens relatively quickly. And I'll show you that both from the conventional maps that we get from NCEP and Pete processes nicely for us, and also from Viz 5D. We'll take a look at some of that.
Look at that cellular convection over the eastern Hudson Bay.
Yeah, isn't that interesting?
You don't usually see the Hudson Bay as a warm plate.
That's right. It's two things going on. The water isn't really that warm, for sure, but it's so much warmer than the minus 20 or so air at 850 above it that it looks like what you see off the coast of, the northwest of the United States when there's an upper trough over it. So, yeah, that'll disappear fairly soon. Another month or so, there'll be enough ice on the lake that you won't see that anymore. Okay, so let's take a look at the radar.
Can I point out two things on this image real quick?
Sure.
It's dark at the North Pole.
Yes, it is. It never gets past.
The terminator might be exaggerated a little bit, but it's definitely, there's areas of dark out there. And then just, Michael will be talking about this later, but the smoke off the west coast. There's two big fires going on, one in Northern California and one that started last night north of Los Angeles, kind of right there. I think that's
Malibu, that's right.
Yeah. Is that north of LA? Or right
that's
around?
where Johnny Carson's home is.
Yeah, right. That started overnight or real late last night. So you can see the two different plumes. This one's smaller from the LA fire, and this one's huge from the one yesterday.
And the characteristic clearing along the coast, which is part of the synoptic setup for the fire conditions there. There's usually ridginess and cyclogenesis in the interior that drives those fires. These are Santa Ana type events. Even though we're a few weeks past the maximum for that.
They're downslope windstorms. They're downslope windstorms.
Yeah. And that's what Santa Ana is.
Really and good news, we're getting very close to GOES 17 hitting its GOES West location and becoming not operational, but available. So within a week or two, we may have this kind of imagery over the Pacific.
Have they solved the problems of heating?
They have not solved the problems with heating. They have mitigated the problems of heating, and there are times of the year where we'll get really good imagery. So all of the visible bands and the shortwave infrared, which is what we'll be looking at for the fire weather later, are available 24/7 all the time. All of the infrared bands are affected. Some are affected to a worse degree than others. The water vapor channels in particular are very bad at times of the year. Right around the solstice, they're better and available almost 24 hours a day. Right around the equinoxes, they're pretty good. Near the winter and summer solstice, they're affected pretty badly.
What difference does it make way out there in space?
What's that?
What difference does it make? Perihelion of the sun? I mean, I'm not sure. They're gonna.
It matters whether so the problem is the detector, the ABI detector that does this stuff has to be kept very cold. That's what the cooling issue is. The coolant is blocked, they think, and it's not keeping the detector cool. So when the sun is shining into the detector, it's counterintuitive, it happens at night, right? When it's in the daytime, the sun is behind the satellite. The satellite is between the sun and the earth. So the detector is cooled by the satellite itself, and you get good imagery during the day. At night, when the sun is on the other side of the earth shining into the detector heats up to the point where it's no longer getting good imagery for some of the infrared bands. That's what the problem is, and that's why it's varying on the time of the year, or dependent on the time of the year, because near the solstices, the sun is up above the earth. I mean, in terms of where it is, it has to do with when the sun is shining into the detector is when the problem is bad. So there are times of the year when it's bad and times of the year when it's not as bad. And I'll try to include some of that information on the page, because I'm sure we're going to be getting imagery saying, or questions of people looking at it and saying, hey, your imagery is bad. It's like, yes, I know. And we're giving you the good imagery, and you'll just have to deal with the bad. There's nothing it's not like you can just fly a space shuttle out 22,000 miles and fix it.
Yeah.
Can we look at the water vapor to see some of those
Yes.
cyclones? Do those show up on the?
I don't know. I didn't see that this morning. I spent a lot of time looking at this 5Ds. Yeah, there's a little bit of something going right along there, but yeah, sometimes when you have a fairly active period, you can see a whole bunch of little vortices in the flow. I think maybe the factor is it's just so cold. I don't know if that's the case or not with the water vapor satellite.
If it changes anything in color.
No, I think closer.
You don't really see anything. Sometimes you do see things in the northwesterly flow, but not this time. And nothing as dramatic as you will see at some point during the winter. There's no doubt about that. There's just nothing there. Let's take a look though at the infrared over the west coast of the United States, so we can see what's going on there. Aside from the fires, which we'll talk about separately, but there's a very nice little cyclone to the north of Hawaii, maybe about Midway Island. Nice cloud mass associated with it, but one gets the idea that things are elongated north-south in a fairly dramatic fashion here, as all the clouds are headed straight into the Gulf of Alaska on the warm frontal portion of this, and then streaming at about the same longitude northward along the cold front. So this is kind of a stretched out, meridionally stretched out cyclone. And yet it's got some convective activity in its vicinity. I don't know how deep the cyclone is here, but probably not that particularly impressive. And then the west coast is clear, largely, especially off of California and northern Mexico, and that you'll see as part of the synoptic setup for the current day. There's a big ridge kind of over the western United States, and that has promoted anticyclogenesis inland, and so there's offshore flow, which tends to make it clear along the coast. Although various disturbances riding over the ridge crash southward, and here's one with the cloud mass trailing across the states of Washington, Montana, and Idaho, and maybe this, whatever there is of a circulation center, may be up in Alberta somewhere, as it rides over the ridge. So that's a broad overview of what's going on in the eastern Pacific today. So let's take a look at the continental radar, if we could. So it's been raining on and off a lot of different places along the East Coast for much of the last couple of weeks. It's been one system after another. I don't know how much Philly got for rain yesterday, but was it well over 7/10 of an inch or something like that? I don't remember. I didn't look that up. Anyway, continued moderate rain across parts of Pennsylvania, West Virginia, Virginia itself. Gets a little bit less organized in the southern portion of the Appalachians, and then a little better organized along the Texas and Louisiana Gulf Coast. This is all tied in some way to a broad baroclinic zone that's draped across the eastern United States on the, well, I guess on the warm side in the cold frontal portion of the first cyclone that's up over Ontario and Quebec, and there are new disturbances to come in the northwesterly flow. And then a lot of the precipitation that you see reflected in the radar over states of Michigan and parts of northern Wisconsin and Minnesota is affiliated with lake effect activity, because it is starting to get much colder and the flow is coming in off off of the lakes. I think Milwaukee probably had more than an inch of snow this morning than we did. And this forecast was really good. If you look back at some of the GFS forecast panels in the last day or two, there was an obvious maximum along the coast of Lake Michigan, or actually in the middle of the lake, in the forecast panels that was not true back over the central part of the state, and I think that'll be reflected in snowfall totals. So that's a fairly accurate forecast, and one gets a sense that there's a broad cyclonic circulation aloft. We'll see why when we go to some of the upper level charts in just a minute. So that's really the story across the continental U.S. Let's take a look at the 500 millibar map.
Here's the smoke from the LA fire.
Oh, is that smoke?
Yep.
Oh, wow, how do you like that?
Because it never rains in sunny Southern California. It's a 70s, bad 70s music.
Well, unless the Red Sox are raining on the Dodgers parade. That wasn't that long ago even, you might remember. Let's take a look at the 500 millibar Super Pete, if we could. So here's where some really interesting things start to show up on the maps. We've actually got a really intense, narrow upper trough. There's where the cyclonic circulation we just saw on the radar is kind of emanating from. You can see the cyclonic center of the circulation, maybe over western Minnesota. That just about exactly corresponds to what we saw on the satellite. We've maybe displaced a little bit further to the south and east since 6 a.m. or 5 a.m. this morning, 7 a.m. this morning. But look at this upper baroclinic zone. It's really intense. It's minus 39 degrees at Sioux Falls. It's minus 37 at Minot. It's minus 26 near the Black Hills. Minus 28 or something, I guess it is, there in North Platte. So this is really cold air at 500 millibars. It doesn't often get much colder than this. Even in the depths of the winter, you don't see it colder than about minus 47 or something at these stations. So this is about as good as it gets, and it's only November 9th. And you've got this really intense baroclinic zone, an extraordinary horizontal shear. You've got 90 knots, 95, 75, juxtaposed with 45 and 40 and 50 to just to the north. So there's really strong shear in that location and really strong horizontal temperature contrast. And we'll see in a few cross sections what that actually looks like in the vertical as well, not long from now. But a really intense curvature maxima too is at the base of this trough, with the jet streak probably right there as well at the base of the trough. So we got a cyclonically curved jet, and that is a recipe for interesting weather downstream in time, but not always in the same sequence from one case to the next. So that's a really interesting feature, and it's developed over a period of time that some of it I'll be able to mimic for you by looking at the Vis5D that was from the GFS initialized at 0Z on the 9th of November. Maybe we should, before we quit this, Pete, let's just take a look at the last several maps. We won't have to look at the whole week's movie, but I know we'll have to load it. We'll just look at the last several, just to get an idea where some of that structure comes from. And this was, here's the beginning of the prior disturbance, a pretty strong upper front across Texas and Oklahoma. That's kind of now left a baroclinic zone along the coast as the days have gone by. So there it is. And then you're going to look in the northwesterly flow over the archipelago. So here's the other major synoptic feature over North America, a giant ridge, which pokes its way all the way to the north slope of Alaska and the northern coast of the Yukon Territory, and then strong northwesterly flow across western Canada. And this is 0Z on the 7th, so this is Wednesday morning. I don't believe there's a 210 knot wind at Halifax at 500 millibars, so that's interesting. That just doesn't seem right. That doesn't seem right to me. Let's keep going forward. Good. And one begins to see a little bit of confluence between the flow around the ridge and the flow around this deep depression to the south of the archipelago. That confluence starts to concentrate in the baroclinic zone over like Great Slave Lake. Here we are at 12Z on the 7th. Let's keep going. A little bit more concentration, a separate little shortwave, broad though it might be, just the south of that lake. And you can see the temperature contrast getting more intense. It's minus 35 to minus 23 across that zone. Going, Pete? So this is 12Z yesterday, and there's our baroclinic zone. And one sees, again, a continued region of confluence right on top of it, minus 29, minus 42. Minus 23, minus 42. So that's really, really cold air. And then the next one is the 0Z map. And you can see that's when the upper trough was just over eastern Montana, the Dakotas, and northeastern Wyoming. And beginning at that time to generate ascent week though it was, to its east, and then some of that came over us last night in the form of snow. And so we had a little bit of the snow from this wave. But it's not the one that really drives the subsequent development, I don't think. You see that when you go forward in time. So that's the current now, as you just saw. So let's go to the 300 millibar analysis and just this current time. We won't look at the movie of that. And so here's the jet streak, the polar jet streak in the northerly flow, northwesterly flow. And then this is the subtropical jet that's out to the east of it. And it's really interesting. When these two come into close proximity is when the upper vortex structure for this wave really starts to take some shape. And we'll see that in this 5B. And then if we could, let's take a look at, just to confirm that that's a subtropical jet to the east. Let's go to 200 millibars. Yeah, so it is the same structure. So, and there's absolutely nothing in the northerly flow. So this is, that feature draped across the eastern United States is tied to the subtropical jet. And look at where it goes. It goes way up toward Iceland, but it's still really part of that structure. How about at 850 millibars, Pete? Let's see what the baroclinic structure looks like in the lower troposphere. So here's our cyclone. Remember, our upper trough is right about in this location, and so it's immediately downstream of the upper trough axis that the lowest geopotential heights exist over the northern part of our own state and upper Michigan. And look at the cold advection back behind it to the west. The temperatures are in the low minus teens over the Dakotas, so minus 19, minus 16 at International Falls. But there's a broad region where the air is homogeneously that cold and not much colder. Look at it, it's over the whole region of the Dakotas, Minnesota, most of Ontario, most of Winnipeg, Saskatchewan, no, what am I thinking about? Winnipeg, huh? Manitoba, Winnipeg, Manitoba, and then parts of Saskatchewan. So a huge area of the north central part of North America is uniformly cold at minus 20-ish at 850, and it's immediately to our north and west. So it's going to get worse than it already is. There's almost no way to avoid that fate. And it's a really interesting but not well organized structure in the lower troposphere over the eastern half of the southern part of North America. So here's the one cyclonic disturbance right over us. Then there's an extended minimum in geopotential height that takes on maybe another maximum in vorticity over West Virginia. And then there's the cold front associated with the prior disturbance and aligned underneath this subtropical jet that is in the eastern United States. So there's a cold push. There's an already pre-existing frontal boundary that has some dynamics. There's about a 90-degree wind shift across that, so that's frontogenetic. And a little bit of a thermal ridge over Pennsylvania, New York, downstream of this development all by itself. And then there's a broad anticyclonic flow over Ontario. So it's a lot of interesting pieces in the eastern half of the United States, waiting to be organized by whatever happens a lot.
So John,
yeah.
So over like southern Lake Michigan, southwestern Michigan, and south, there's a vorticity maximum probably there, or maybe even southeast of there. So a little bit to the
oh yeah, right in here, yeah,
right in there. So
yeah,
you already have a little lower tropospheric vorticity maximum, and then the upper vortex.
Yeah,
so
yeah.
Nice interaction between.
Yeah, that's right. And the interesting thing about the lower tropospheric vorticity structure is it's kind of not put together very well. So the upper trough is going to somehow pick which one of these features it's really going to grab onto and then develop. And that's kind of interesting. Probably makes the forecasting difficult, especially it would have been in the era without trustable models. You'd say, oh boy, I know something's going to happen down in here, but it could either be this disturbance or it could be this one. And that makes a big difference about who gets what weather. So tricky forecasting. Okay. And right along the Rockies, this is somewhat artificial, but not entirely, right along the Rockies and in the immediate lee of them, you see that's where the strong temperature contrast is, because this is the western edge of the cold dome. And it's not only at 850, it's at a variety of levels. Okay, could we go to Viz 5D, Pete? And I've put that up here, and so let's see. There's the control. Great, thanks. Oh, just before we do that, I guess I'll get rid of this. Yeah, let's do that. This one right here. This is our up-to-date 850 millibar cold pool analysis. So the 1948 to 2014 averages in blue. Here's the daily time series for this year. We had the 20th warmest September of all time, so that was mostly this bubble right here at the end. The last 10 days or so of September were pretty warm relative to the long-term average. This October was just about consistently parallel below this value of the climatological average, and accounted for the 6th warmest October. When you put them together, this was the 11th warmest September, October in the 71-year time series. So, and there we are. We're making steady progress at exactly the same rate of increase of area, but at a smaller value. So this seems to me to suggest.
So Asia must be pretty warm.
What?
Asia must be pretty warm.
It was, especially mostly in October. I don't know what's happened in this first week of November. There's been a little bit of a creep towards climatology.
Is there much variability? Is that normal that, in fact, they're almost parallel or, you know, roughly parallel with blue and red curves since October 1st? Or in most seasons, do you see it flipping a much larger cold winter?
I don't know. I've only just in the last 2 years started looking at the run up to winter, because winter for me starts December 1st. So I don't really know much about the history here, except insofar as a comparison to climatology. That's a really good question. I suspect it's probably harder for the hemisphere to have big excursions upward or downward, and instead it just kind of climbs at a steady rate. The question is, does it get fitted for the winter early in the season? So in other words, do we expect that if it gets off to this kind of a warm start, that there's going to be some tendency for that to be sustained throughout part of the winter anyway? I don't know the answer to that either. So, but anyway, I just like to show you this every couple of weeks, let you know where we are.
John, one more thing.
Yeah.
Seriously, where that dip happens right before the beginning of October, is there any way to like figure out if there's actual some regime changing there where it was really following the blue line and then it suddenly kind of dips?
I suppose, yeah, I suppose you could. I remember just this, I'll have to recall anecdotally, but I remember that it was quite conspicuous, and I have the movie for the whole season every 6 hours, so you can look at it. But it was quite conspicuous that there was absolutely no cold air in Mongolia and Siberia in that last week or so of September. And it's not as if it had already been established either. I don't want to suggest that it was there and then disappeared. It just might be that that's the time of year where it finally does get established there. And in a normal year, that would account for a larger area in the blue. But this year it was absent and it never recovered in September. And then that extended into October as well. So, but eventually it's now cold in those places, not quite to the climatological level, but something's gotten established there. But there was a conspicuous warm anomaly in the last 10 days of September over very odd places, Siberia, Mongolia being the ones that caught my eye. So that's interesting. I don't know. Was this a regime correction and then if you fit the winter right there? I don't know. We'll have to wait and see. Okay, let's go to this 5D if we could, Pete. So here is the pressure every 4 millibars at 5.4 kilometers. This is from last night's run of the GFS 0Z on the 9th of November. And so you can see here's our little shortwave that was the one that kind of was influencing our weather over the next 12 hours or so. And geopotential height gradient, or the pressure gradient's largest here over Montana. So this is the local wind speed maxima too. I won't show that, but you can make that intuitive leap. But if we put potential temperature on there at the same level, you see that it's also, that shortwave is also associated with a pretty intense baroclinic zone across the flow. So that's interesting. And that baroclinic zone's intense all the way up into the Northwest Territories of Canada. So that's a fairly continuous linear feature on the western side of the northerly, of the upper trough. So that's the western side of the cold dome. And then here's the broad baroclinicity. This is every 2 degrees. The broad baroclinicity left over from a trail of systems that have cut across the eastern United States over the course of the week. And we saw some evidence of activity along the southern end of that this morning. So I don't know if I've got this loaded the right way. Let's take a look at the cross-section of potential temperature. Good. And we want to cut it so that it's like that. So just move it up, I guess, a little bit, Pete, if you could. That's going to be good enough. And then we'll do the same with the PV. Slide that up there. And then one last one is vertical motion. And I've already got it all set up, so we'll get it on there. Okay, let's do them one at a time, though. So let's look at just theta first, and then just flip this up, get an idea what the structure looks like through that baroclinic zone. So it's a pretty intense upper front, and it even seems to have its feet kind of beginning to find the ground in some of these isotopes, like the 294 isotope almost makes it to the ground, not quite. But at this time, 291 or 288 makes it to the ground. But there's a pretty decent upper frontal zone. And what does it look like in the PV? And it's a stratospheric intrusion, but not a really dramatic one. But it's definitely down below the PV greater than 1, characteristic of stratospheric type values is down lower than 500 millivolts. And so we have an upper vortex structure associated with this upper front. And what about W? And I'm only showing the subsidence. And one gets the impression right away that here's an axis of maximum subsidence coming right along these isotopes underneath the jet, which would be right about here. And that's going to be dragging the PV to further and further lower elevations along the isotopes and intensifying the upper vortex structure over time. So that's a pretty nice picture of an upper front actively becoming more intense. And that is, if we can remind ourselves where we are on the top view, and that's back here in this northwesterly flow state. So that's 0Z yesterday. So let's march forward a couple of times, Pete. Pressure's right there. Yeah, so let's march forward a couple of times. I think we'll go to maybe 12 hours ahead, so that'd be this morning, 12Z. So let's put theta on there. We won't stop and do it the same analysis every time, but one can see there's still a fairly continuous baroclinic zone all the way from the northwest shore of Hudson Bay down into Kansas, Nebraska, arguably into Illinois. And it's most intense right about where one imagines, if we take theta off just for a minute, you can still see sort of a local maximum in the pressure gradient over South Dakota into Wyoming. So that's probably the jet streak maximum at 500 millibars, and that's about where the temperature contrast with theta back on was the largest. So that's a consistent relationship that that doesn't go away. Now let's keep on going to maybe noontime today, so right about the time we're at now. And there we are. So let's take pressure off for a second, Pete. I think you can start to see some of these isotopes have irregular shapes the closer they get to the bundle. Like look at this one, 304. Comes in and then suddenly decides to move closer to the bundle in eastern Nebraska, central Nebraska. 308 does the same thing in Kansas. And then 310 does the same thing. It gets into southeast Kansas, and instead of going straight along, it kind of gets adhered to the edge of the baroclinic zone. And that's because there's subsidence that's occurring in this location, intensifying that upper front. So let's prove that. Let's take a look at a cross-section through Missouri. We'll have to rearrange things. Maybe we'll do it like that, I guess. That should show a pretty good one. And we'll put all 3 of the variables on there, although only look at one at a time like we just did. Thanks, Pete. First, let's look at theta. And so that's a pretty decent structure. Again, looks rather similar to what it did before, although it's more obvious now that some of the same isotopes that are part of this upper frontal zone are hitting the ground as also part of a pretty intense horizontal baroclinic gradient. Let's put the PV on there. And we get a steeper tropopause on one side, and there's the PV, a larger area anyway. Probably that means a larger volume of air from the stratosphere is underneath the 500 millibar surface and producing pretty large values of vorticity. And then the vertical motion, really intense subsidence. This is 1 centimeter per second, and it's right through the jet core, which is not indicated because it just gets too messy, right through the jet core, biased to the warm side of the baroclinic zone, and then down along the sloping isotopes. This is a period of really intense development of this feature. Mike?
So John, how do you reconcile the subsidence, which is, I guess, associated with the sort of extrusion of a high PV into the upper troposphere, below that purple level that you have there, and that should be also associated with a cold dome beginning to expand upward, right? Because you bring the PV down, it's going to get more anomalous, so it should get colder
underneath to the east, right? So it's
like that. Is it just are we missing vertical motions? So it's not in this cross section we see them as robust, but significant ascent that would be associated with the vertical advection of those isotopes upward.
That's a good question. I guess there's 2 possibilities. One of them is remote. I don't think we have the bad cross section angle. That can sometimes lead you to think, what's going on? Why is it so flat over here? That would be guess number one, which I think I would dismiss on the fly because I think I got it at the right angle. So I don't know if that's what would be the second guess about that you have about the lack of upward vertical motions. I wonder what's going on there.
Yeah, I don't have a sense of it. But the other curious thing is, as you're bringing that potential vorticity downward, if it's being vected downward, and even under, I guess, to the right of the region where we see the subsidence.
Yeah. This is a little bit off phase.
But in that region, I'm wondering what the vertical motion should look like, and that suggests subsidence. But if you're going to bring these isotropes upward, what's the mechanism? Is it vertical convection?
You mean to build a dome here?
Yeah.
Yeah, I don't know what the answer is to that. I thought you meant down in here. You can have all that is required to build the upper front is differential vertical motion. So it can all be subsidence, just stronger in one place than another. But to build the dome is, I don't know, it's a good question. It's a deep, cold air dome already. So these are really cold temperatures of the ground. This is well below 268 or 265 Kelvin already. So it's really deep. And you can see a little bit more evidence of its dome structure on the eastern side than you can on the western side.
So I wonder if it may be a very obvious answer, and I'm just,
yeah, I don't know what it is off the top of my head.
But it's something that's always sort of puzzled me about how these structures come together.
Yeah, this is not an east-west cross-section, don't forget.
No, it's north-south, that's right, yeah, it's north-south, that's right. So that's a good question. So let's go back to the top view, and let's put vorticity on top of this, which I've got set up for QZ, and we'll take the theta off. So we did this without, here's the vorticity, absolute vorticity, 12, 16, 20, 24 times 10 to the minus 5 over southwest Iowa, northwest Missouri. So that's the beginning of the upper vortex structure. I want you to click a few times ahead, Pete, and that's tied to the upper front. I think let's keep going. I'll know when I see it. Yeah, one more. Yeah, this is the time I'd like to stop at 12Z Saturday morning. So the same contour interval, this is 12, 16, 20, 24, 28, 32. So now we've got a long strip of upper vorticity at the same elevation that has gone from 2.4 times 10 to the minus 5 to 3.2 times 10 to the minus 5. The question I had was, where did this air come from? What is this all about? How do you get this upper vortex structure? So let's go to trajectory mode. And I'm going to show you that, let's click on number 2. That's the front edge of this upper vortex structure. So the air that arrives over Lake Erie at this time, or near Lake Erie, has come from that location. Step number 4 is in the middle of that strip of high vorticity. Where did that come from? Looks like roughly the same place. And then 6, that is on the southern edge. Is it 6? I had a whole bunch of them. No, it's not 6. It must be 7. Sorry. And 7 is on the southern fringe of that long strip of upper vorticity. And that seems like it came from all the same place. Let's go back to the beginning and animate this. And we can take the vorticity off if you want. But in fact, let's do that. Yeah. So this is all coming in northwesterly flow, and then it's a couple of swirlies because this starts to be cyclogenesis. But up to this point, where does that air come from? Let's take a look. Let's stop it at this point, Pete. Once it gets to the first swirly, because the swirlies start to make it look a little confusing. Now let's just tilt it up. Let's see what happens. So it's all subsiding. It's all coming down from about 7.8 kilometers down to about 5.4. And that is, we'll see in a minute, where is this located? Where is this subsidence located? Let's go to the top view and start near the beginning. Good. That's good enough. And let's put theta back on there, horizontal theta. And let's find out if we're at the right elevation. We're not, I think. We have to lift that up to a higher elevation. So let's check that out. Yeah, we're not quite high enough. So let's go up to there, which is about 8 kilometers. So let's see where we are relative to the temperature structure. Don't go too high, because if you go into the stratosphere, we end up seeing a temperature reverse. So right there is perfect. And then let's go forward a few times just to see what we see. So we don't see any evidence really of the cold dome. I guess it's cold right here over Hudson Bay. If we were to look a little bit lower than this, And that's why I wanted to start at this elevation, just a little bit lower than this, and put theta maybe half kilometer lower or something. Then you can see the baroclinic zone starting to show up. So this is all a northwesterly flow subsiding. It's on the western side of the upper cold dome, and it produces a really impressive upper vortex structure, which if we can go back to the 12Z on Saturday, and I'm almost done. Stop there, we'll get rid of this theta. This wasn't particularly illustrative. I think I had something else in mind. I can't remember what it was now. And we'll put vorticity back on there. And then one other thing is mean sea level pressure. And I have only MSLP. I have only 1,012 or lower on there. So look at where we're going to get our development. This is 1,004 millibar low, immediately down shear of this strip of really large vorticity. Let's just take the trajectories off for the time being, and then click through, watch how that structure evolves. Good. We can click forward, yeah. So here we go with development going on. There's 1,000 millibars in the middle, right at the front edge of this upper vortex, 996, 992. So you see how that's going to work out. That this upper front has produced this deep tropopause structure, and it's down shear of that where your upper cyclogenesis, where your cyclogenesis is going on. The last thing is PV colored in here, the surface. Why is it not coming up? Save all that.
Values to it.
Oh, that's what we're doing. Yeah, bring it up to 2. Thanks. Oh, I had it all colored too, so we'll just do it by pressure. We don't have to fiddle much with it. That's pretty good. Okay, perfect. And so, yeah, let's take a look underneath. So there's the upper vortex structure that was evolved out of this upper frontogenesis. Keep turning it around, Pete, so you can see that it really just produces a cone of particularly high PV within a trench. And it's right where the cone is closest to the ground that you get the minimum in sea level pressure. And that's a beautiful example of how this upper frontogenesis leads to the development of this upper trophiness. And then down shear of the trough, you get this massive explosion of cyclogenesis in eastern Canada. It's going to get into the 970s by the time the weekend's over, up over Quebec. So it's a pretty nice example of the robust dynamics that go on in the cold season. And we got a really good example of it over us right now. So I think that's all I have. Melissa.
Looking at these, it looks like there are a lot of kind of similar depth protrusions into the troposphere.
Yeah.
Only one cyclogenesis event because the PV wall is the strongest in the location that we've been emphasizing.
That's right. That's right.
That is.
That's right. So you've got jet circulations, you've got vortex dynamics, all of it's kind of concentrated in one broad region, and that's not true for all these smaller scale disturbances. That's right.
And probably, I would argue maybe a slightly more, a more significant feature, or what's missing from the other ones might be lack of any baroclinicity for them to interact.
That's true
with,
also, yeah.
To help deepen it.
That's true also. So in this thing, the thing that I find interesting about this, if you look at the conventional 500 millibar vorticity maps, it looks a little more obvious in the PV, which is one of the advantages of looking at it this way. It takes a long time for the 500 millibar vorticity to suddenly gain a large value. It happens within a 6-hour period. And it's really part of a long-term progression of subsidence from the stratosphere that drives that, is what I think.
Right, but I'm also, another part of it is also the fact that you have the cyclone itself spinning up. The lower tropospheric circulation there is going to have an impact on 500 millibars, right? The warm seclusion that forms and the warm anomaly at the surface has a cyclonic circulation that helps to contribute to the 500 millibar vorticity.
Yeah, that's true. Although the cyclogenesis doesn't really start in this case until you get that 3.2 times F vorticity structure. It's really weak until then. So it does seem like in this case, you don't get anything happening at the ground until this thing is kind of almost fully mature. But it does certainly interact once they get going. Yeah, so I thought it was an interesting case. Okay, thanks, Pete, for expert driving through Viz 5D. Never easy.
This will be just a very brief description of some of the forecast as it evolves, and I'm going to begin collecting a set of maps that will Of course, I'm not going to be able to talk about it here next week, but we can be anticipating what Thanksgiving might look like in terms of weather. So, and also, while that's coming up, or perhaps coming up, you could also bring up, you can go to the webpage for the Weather Watch. I have a list. I'm going to go to the hazards page. That's the expert assessment page. Yeah. And we'll go to hazards outlook. So this just shows these are U.S. hazards over the next week and a half or so looking forward. A couple things to first note are that in the western part of the United States, particularly in northern California, Oregon, and then into the sort of Intermountain West, they're experiencing a severe drought. Now, over the last several years, California has been abnormally dry, but at this point, most of California isn't in extreme drought or severe drought at this point. But the southern part of the state is, northern part of the state is, and we'll see with that dryness, it enhances the possibility, even in places that aren't in a severe drought, for significant fires if there's some spark to ignite them. But other hazards that are expected to come up over the next week or so, starting in just a couple of days through the 15th of the month, in this dark blue area right here, this is expected to be well below normal, much below normal temperatures here. Possibility of heavy snow in the northern part of the U.S., just north of Lake Superior to just north of Lake Huron, and then in the northeast United States and in the northern Mid-Atlantic, possibility of some heavy snow, heavy rain forecast for the east coast of the United States later on, and the possibility of some flooding, perhaps even in southern Texas. So with that in mind and knowing sort of what's going on, again, this isn't a drought area, but we're going to look at two significant fires that are occurring right now. The first thing I want to do is go to this first image. Pete, you had, I think the one you just brought up, I think this one. This is from a Landsat image. This is a fire that's near northern part of California. This is the Camp Fire, Butte County, California. And this fire was actually spreading at a rate of about 60 football fields per minute yesterday when it first started. And then this is, again, Landsat is, I believe it's a polar orbiting satellite. And so you're sort of seeing really high resolution imagery of the smoke plume that we're able to see in the imagery that Pete had just earlier. You can even see some of these populated areas right here. Over 2,000 structures have already been destroyed from this fire as of this morning, and it's going to continue to spread. And part of this is, again, fueled by the fact that you have dry fuels, vegetation that's grown over time, that's died out with the dry weather. Again, not a severe drought for this part of California, but they are experiencing relatively dry weather, very dry air over them at this point, and you have those fuels, anything that can spark it is going to start it. I don't know what the cause of the trigger for this fire was.
It just started yesterday, right?
Right.
So 2,000 structures were destroyed in a day.
Right, and spreading at a rate of 60 football fields a minute.
One per second.
This is
It's explosive.
explosive. If we go to the next satellite image, this just is IR enhanced. It will show you the, not this one, the other one that says campfire on it. Right, this just shows, based on the IR, it's getting some temperatures indicate where the fire actually may be at this point, just to give you a sense of that. So it's somewhat enhanced. Natural colors with IR highlights. They're using the brightness temperatures to come up with a sense of just where the fires actually are. So you can see that really interesting smoke plume directed generally toward an offshore direction toward the southwest. If we go to Pete's page, Pete's image, the satellite image that you had up there, Pete.
This is the Zero one from Colorado.
Okay, so this is Sierra, right? So this is another image. This is from the GOES imagery is from Sierra. These are Megitis. You can sort of see again based on the air imagery. This is where the fire is. You can see that smoke plume. This is Lake Tahoe right here, and you're going toward the Bay Area. Some of that smoke going there, but being transported offshore in a northeast with a northeast wind. You can see how it got triggered and this huge smoke plume that forms. And you've created a couple of images.
Yeah, I think this is the visible one from me. This is the 1 minute mesoscale imagery. So here you can see the smoke from that fire yesterday. And I think the other one starts here late in the day.
Another one there. there it
This,
goes.
there it is, that's the other one.
Right.
That was the visible loop from yesterday. There's this one, which is the 5-minute imagery starting before the fire, just to show how quickly it spread. This is every 5 minutes. And you can see the other one start down here later. Right.
It's nice use of remote sensing instruments to
Huge area.
take these. Yeah.
So the yellow, the black into the yellow to the red is very hot infrared temperatures. And at this time of year, likely fire.
Right. Okay, so what's we saw from the forecast maps, let's go back to your page, maybe go to 500 millibars, just again, and then look at us. Well, actually, 850 millibars. Super. Yeah. Just with a broad setup. And what typically happens, and this isn't, I guess, a classic Santa Ana setup. The Santa Ana winds are generally associated with an offshore flow with a big anticyclone over the western part of the United States, one that's quickly developing. And as the pressure gradient increases between the high over the inland areas and lower pressure toward the coast, you get this flow that's directed offshore. Suggest this perhaps is not the most significant one, but these are conditions that are similar to what you see with the Santa Ana. Typically, these occur in October. This is a little bit late in the season for this to occur. But again, with very low dew points and high dew point depressions, that dry air is just going to make the fuels for fire easy to be ignited, and then you get these significant fires. And if the winds are really persistent, they can help spread the fire really rapidly. I don't think there's any evidence of really strong winds. Greg, you're saying that there may be some downslope wind, a windstorm?
Well, that's what Santa Ana are.
Right. I guess I haven't heard much about significant gustiness in the winds at this point, but for them to spread so rapidly, that's probably.
Well, you can see the smoke that they're pretty strong easterly component of it.
As it gets up to some modest elevation. Okay, so I just wanted to show that, show it off, but let's come to the, let's go to the, no, I don't think that's run, we can check once, but probably not going to come out.
The broad subsidence associated with the upper frontal environment is also contributed to the anticyclogenesis that sets up inland.
Right, so you're getting that big, yeah, right, with the, on the western side of that upper trough.
Yeah.
Subsidence there, that's to help build the ridge. You can see the primary ridge is right over here over the Dakotas and eastern Montana. There's a secondary region of higher pressures that are right over the Idaho and Utah. And you can definitely see that northeasterly flow.
Yeah, the pressure gradient there along the Sierra Nevada is huge.
So, looking forward in time, seeing the development of the cyclone that John was referring to, we saw that sort of area just to the southeast of the primary cyclone over Michigan. In this region right here, right along a nice baroclinic zone, the upper wave that we can see evidence for in the thickness field is right there. This is valid at 18th east of noon today. And you can see the cumulative precipitation ending at this time period is all to our east. And if we step ahead just 3 hours, one click ahead, we can see that precipitation edge continuing to move pretty smartly off to the east as the precipitation winds down. But you can see here in the thickness advection, well, there's not much cold advection occurring right now. We're pretty much as cold as you can get because the gradient really relaxes. It's a little bit colder to the northwest here, but there's not much more transport. All the significant cold advection is well more south at this point. But you'll watch here. Here's the 1012 contour. If we just step forward in time, you can see that rapidly the evolution of this cyclone begins to deepen from just under 1012, and now we've lost at least 4 millibars of pressure there, down to 1008. About a 12 millibar drop at some point. This is down to 1004, it's another 4 millibars. 1000, I think it's still going to get down into the 990s, just in a few more steps. 998, and then down to 990s, just under 996. So that cycle begins to rapidly intensify.
Now, the football game
Right.
is 6 hours from like that time. I mean, this is 12Z, right? Football game's about 18Z.
That's going to be
Penn State.
Penn State.
Oh yeah,
Happy Valley.
Happy Valley, right? The windy Happy Valley,
Yeah.
cold advection Happy Valley, but I don't think they talk about cold advection on the news. Right, so it's gonna be a windy day there. You can see that from the gradient and pressure, and there may even be a few snow showers. I mean, there's gonna be lake effects certainly from just south of Rochester, near Buffalo, and then just northeast of Cleveland, or yeah, to the north and northeast.
Go ahead
of
6
Cleveland.
hours.
But if you go ahead 6 hours, yeah, the snow bands are still in this region, but not much showing up here. But yeah, it's not probably too surprising. It's gonna be a cold game. This is 18Z, so this is noon tomorrow. The high by this point is crested over our region. Winds are gonna be relatively light, but this is gonna be a chilly day, certainly for us. We're not gonna get much colder than we are today, but I think we're gonna just have very light winds. With the bright sun, it might actually feel pretty nice outside, even though it's still gonna be pretty chilly. And our cyclone is now deep in, it's 998, 996, 994, so it's pretty much over at that point. But this really is a quiet period that's being forecast by the models. We go ahead, let's just go ahead to 32 hours, 6 hours later than this tomorrow evening. The ridge is now shifted. We have warm advection beginning to develop as we have the high now shifted to our southeast. Winds out of the southwest over us begin to warm up. But this is relatively dry. It's air that's being transported northward ultimately is going to have to ascend great distance before it actually begins to condense and actually so light precip, light snowfall to our north. Going ahead into Sunday afternoon, light snow to our north. We got a pretty quiet weekend. I don't want to, yeah, I think it's just cold over the next couple of days. A few more clicks, we'll just look ahead. Let's go at 72 hours, Monday morning. Again, still cold, back into some cold advection as that weather system has passed by, but not really cold. But here's the beginning of the storm that's going to affect the eastern part of the United States. Really wet as the subtropical, as the sort of a subtropical high is now developed. That high that's moving southeastward is now just off the mid-Atlantic coast, and the return flow around it's beginning to, the Gulf begins to open up. There's 72, another really wet. So you saw that in the medium range, sort of the hazards for next week. Here's that region of really heavy snow, rainfall, and on the northwestern edge of it, it is certainly cold enough for snow all the way down to Arkansas. In fact, as this develops, we just stay cold, breezy and cold. Wednesday next week, rain's over, and we'll begin to warm up again. One thing I did want to look at without going through this forecast, and let's jump ahead to 276 hours. And let's go ahead, 300. I want to get to the beginning, and I probably should have gone 324. Okay, no, we skipped it. So 312, this is going to be for Thanksgiving morning. Maybe it's more interesting. Go to 300 hours and stick with that. Go back. So this is we're forecast to have a pretty significant cyclone. If you believe this forecast, we're going to look at a lagged average set of forecasts just to see how this is going to evolve over time. This is actually relatively new, entered new into the forecast. But a fairly significant storm that could affect travel. This is going to be Wednesday evening as people are heading back home for Thanksgiving break. If this were to verify, you know, if you're taking Delta to Minneapolis, you're going to have some problems. Probably just north of Minneapolis, perhaps heavy snow and ice fall to the north. Heavy snowfall expected in this region. Rain for here. Chicago's probably going to be affected by any weather, right? In this case, if it's bright blue skies, they probably get affected by that. Atlanta, again, with this cold front that's going to be passing through that area. So that's the forecast then. But let's look. See, this has always been in the forecast. We go to the 6Z, well, not the 6Z, we'll go to the 0Z forecast. Something like it, a little bit warmer here. Okay, less threatening. This is all valid at the same time, Wednesday before Thanksgiving. And I'll collect these images and maybe leave them with John to just look at them on Weather Watch next week. Go back to yesterday, nothing. Wow. All right, so that's a totally different shift in the forecast. Will this maintain itself again? That looks like a pretty nice day. The day after for Thanksgiving being really nice. You go back to Wednesday of earlier this week. Chilly, but not a problem. So in the last couple of forecast cycles, we've seen the introduction of this significant central U.S. cyclone. Will it last in the forecast? And we'll just watch this. I'll get collecting images that can be looked at for Weather Watch next week. And maybe the Weather Watch following Thanksgiving, we can look at them all and just see what happened. Yeah, we trace that out. We've done that in the past. It's kind of a curiosity. Anyway, so this weekend, cold for the football game in University Park, Pennsylvania. It looks like it's going to be a windy and cold day with maybe a few snow showers possible. But for us, just a dry weekend, but the colder ones we've had since last March and April. So that's it. John, thanks for a really great discussion, and Pete for driving and getting these images up.
Have a nice weekend.
Thank you, Mike.
Thank you.